So welcome to session number 5 of the module 5, wherein we are discussing about design of power screws. So in the previous sessions you have seen the concepts of power screws, how to analyze the power screw, and also we have seen the stresses developed in the screw rod and the nuts. So in this last session we will try to design the whole screw jack system here. So the screw jack, it is designed, it's a self-locking device, power screw, and you have to design it to lift a load of 42 kilonewton, and the height it has to move is 150 mm, and the strength or the stresses, allowable strength or stresses in the screw jack or the screw rod is given here. So in tensile strength, the allowable tensile strength is 82 megapascal, and the shear strength allowable is 50 megapascal. So you have to make suitable assumptions and you have to design the whole of the screw jack here. So usually in the examination will ask you to design the screw jack with some load given and the lift given, and the strength material property will be given with respect to tensile strength and the shear strength. So here already the allowable strength is given, so no need of factor of safety. So with respect to this problem here, so in case if they give the material property, tensile strength and the shear strength, and factor of safety is given, then you have to initially calculate the allowable stresses, tensile stresses and shear stresses in the material, and then you should go for designing process. So here this is a given data. So load is nothing but W in our equation, or the F, and this is 42 kilonewton. So lift is nothing but the linear distance the screw rod can move in the frame, or the lift, the maximum amount of lift it can give, or it can lift the load by 150 mm. And this is the allowable tensile strength 82 megapascal, and this is the allowable shear strength 50 megapascal given here. So in some problems only the material property, ultimate tensile strength, yield strength and shear strength will be given, and you have to consider the factor of safety 3 or 4, and then you have to calculate the allowable strength in tensile as well as in shear. Already in this problem allowable strength is given, so no need of considering factor of safety here. So all of you have known about this screw jack diagram you have done in machine drawing. You learnt about the screw jack, how to draw and how to model this screw jack. So you can see here, this is the main screw rod, and the threads, square thread is there. So you have to select a proper pitch and the diameter for this screw rod here for this particular load, and this is the nut. So it is having internal threads and it will rotate over this screw rod here. So actually it is fixed, the nut is fixed to the frame, and when the screw rod rotates, since it is fixed, the screw rod can move up and down. That means it can lift the load, or when you rotate it anti-clockwise direction, the load will come down. So that is rotation is done by this handle bar or Tommy bar along this collar. So in the previous session we have solved a problem on collar friction, so we have taken the collar friction also. So this is a collar and the cup is there on this collar and the load is applied, so the surface holds the load. So all of you have seen this screw jack, and maybe many of you have used this screw jack to lower the load or up to raise the load here using this handlebar. So design of the screw jack means, first thing is we should specify what is the dimension of this screw thread, what should be the pitch, what should be the diameter, that you have to specify. And anyway the material properties are given, and you have to calculate the dimensions for the screw rod and also the dimensions for the nut here. So nut, you can see the nut and the screw rod, they are engaged with around 4 to 5 number of threads. So this is N. So it is used to calculate the bearing pressure. So bearing pressure is the number of threads engaged with the nut and the screw rod. So the height of the nut is based on the bearing pressure. So that is the given condition, and this is height. So lift of the screw jack is 150 mm. So when you rotate this handlebar, when you rotate this screw rod, it has to move up or down by 150 mm. That distance is given. So here what you can do is, first thing is that since only the limited dimensions are given, data is given, so what you do is we take the diameter, we increase the diameter by 20 to 25% of the combined compressive and shear stresses. So we'll see now. So first let us it is a preliminary diameter. We'll calculate the diameter first. So the diameter, because the stresses are given. So for safe design, so the allowable stress, so the whatever the stress is induced in the screw rod or the diameter or the screw thread, it should be less than the allowable stresses. So for safe design, that is there. So whatever the stress is induced in the material of the screw rod, it should be less than the allowable strength of that material. Only then it will be safe. So that is known. So first we will calculate the induced stress here. So directly we will go to the induced stress or the compressive stress because of the load acting on the screw rod. So it is a compressive load is acting W. So the stress induced, sigma C or sigma induced in that screw rod is nothing but load applied by the cross-sectional area of the screw rod. So AC is the cross-sectional area of that screw rod, which is circular. So the cross section of the rod is circular. So first we'll calculate directly. We'll calculate the induced stress because of this load. The load is known. So whenever you apply the load on the bar or the rod, there will be direct compressive stress. So that formula is load by area. So we can calculate the cross-sectional area on which this load is acting for the screw thread or the screw rod. So it is so the induced stress should be, we design it for equivalent to allowable strength, because the factor of safety is already taken. So we assume or we design it for equivalency. So induced stress should be equal to the allowable stress or allowable strength of the material. So when this is equal, so we can find out the area, the cross-sectional area of the screw thread or the screw rod. So the area is given as 512 millimeter square. We get this. So when this area is 512 millimeter square, we will get the diameter. So diameter is 32 here. So if the diameter is 32, we will get the area so much. So in the data handbook, we will get the nearest standard size diameter of the screw thread as 32. So 32, and based on this diameter, you can get the pitch also. So this is the standard diameter and the pitch combination which is there in the given data for the diameter of 32 mm. So this diameter, as I told you, we have to increase it by around 20% or 25%. So we will multiply this diameter by 125% here. So we will get the diameter as 40 mm. The diameter of the screw thread is 40 mm. And for this 40 mm square thread in the data handbook, the standard size is 40 by 7. So the pitch will take now 7 mm here, and the diameter D1 will become 33, and this is the nominal diameter 40. So 40 minus 7 will give D1, internal diameter of the screw rod. So this is the internal diameter, and this is the external diameter or the nominal diameter of the screw rod. So 40 minus 7 will give 33. And now for this diameter, you calculate the area, we will get the area of the screw rod as 855 millimeter square. So actually we require the area 512 millimeter square, but will increase that cross-sectional area of the screw thread by 25% diameter. So area will increase by to 855 millimeters square. So we have to check for the induced stresses again. So with this diameter and the pitch, we'll check again the stresses induced in the material of the screw rod, and the stresses induced should be less than the allowable strength of the material of the screw rod. So we'll check now. So once the diameter or area is known and the load applied is known, you can calculate the induced stress. So it is again rechecking. So first we'll assume we'll design, or we'll find out we'll equate this induced stress to the allowable strength. Then we'll calculate the area, diameter, and for safe design we'll increase the diameter or area by 25%, and again we'll check the stresses. So obviously that induced stress will be less than the allowable stress. So you can see here induced stress is the load by area. So if you check that, so induced stress or compressive stress will be 49 megapascal, which is very much less than the allowable strength of that material. So you can see almost it is half of that. Okay. So then that means the design is safe. Your screw rod is safe for this load. So coming to torsional shear stress. So torsional shear stress we can find out by first you have to find out the torque here. So once the weight is known and diameter is known, we can calculate the torque. So this formula is there in the data handbook. Directly you can calculate the torque to raise the load, and the diameter is 40 and internal diameter is 33. So you can calculate the mean diameter D2 is 36.5. So the D2 mean diameter, you substitute in this weight anywhere the load is known, then alpha and phi is known here. So alpha you can get it from the friction, the pressure angle you can get it from the coefficient of friction. So that data will be getting from data handbook for this particular square thread of diameter and pitch. The coefficient of friction will be 0.14. So you get it from the data handbook, and once the coefficient of friction is known, the pressure angle phi can be found out. And once the phi angle, pressure angle is known, you can calculate the helix angle also. So it's a single start thread. So lead is 7 mm, pitch is 7 mm, and the mean diameter is 36.5. You can calculate the helix angle 3.49. So you can see here helix angle is less than the pressure angle. So friction is more here. So phi is greater than alpha. So it is self-locking. So your design is safe, and the screw jack is self-locking condition. So that's what is required here. So the phi angle should be greater than the friction angle. So it is only then it will be self-locked. So alpha is less than phi, so it is self-locked. So your design is safe and the conditions are satisfied. Suppose if this condition is not satisfied, then we have to redesign. So you have to take different diameters and pitch, and you have to recalculate, and you have to see that alpha is less than phi. So now torque again, torque required to raise the load is again this equation. So how much torque is required, you can get it from here. So WD2 for this angle. So you come back to this equation again. So you can calculate the torque required to raise the load. So this is anyway in the data handbook. So all the values just now we calculated. Substitute the values, you will get the torque of so much Newton millimeter. So once the torque is known, you can calculate the shear stress. So torque is there, and the diameter, the internal diameter of that screw thread 33 mm is taken, and we can calculate the shear stress by using torsion equation. T by J is equal to tau by R. So R is nothing but D1 by 2. So if you take that, you will get the shear stress also. So it's 22 megapascal. So the induced shear stress is 22 megapascal, which is less than the allowable strength, shear strength given in the given for the material. So again you are safe here. So coming to buckling, so you can go to the buckling equation. It is there in the data handbook, and substitute the values. L by K is the slenderness ratio, K is direction radius of gyration, which is nothing but d1 by 4, and length of the screw rod L is 2 times the lift, so lift is 150. So usually we take the length of the bar rod, the handle bar, as 2 times the lift here. So just assume some data and get the values here. So A is from the data handbook, it is so much for a column free to bend in any plane. So you can take this condition in the data handbook and you can assume some value of A, so much. So knowing all these values, you can easily calculate the crushing stress or the critical stress in bending. So this is the bending column critical stresses which is induced in the screw rod. So you can calculate the principal stresses. So sigma 1 you can calculate. So the formula already you know. So this is sigma C, or the compressive stress, the direct stresses in the screw rod, and this is the shear stress. Just now we calculated this. So from that we can get the maximum principal stress. So it is 66 megapascal. So the maximum stress, direct stress, which is induced in the material is 66.5 megapascal. Similarly, you can calculate the maximum shear stress. So that compressive stress is there and shear stress is there. You can calculate the maximum shear stress, 36 megapascal. So you can see here the maximum stress induced in the material, principal stress, will be less than the allowable tensile strength of the material, 82 megapascal. Similarly, maximum shear stress in the induced because of the load W is less than the allowable shear strength of the material, 50 megapascal. So after calculating the induced stresses, you have to check that with the allowable strength of the material. So the induced stresses should be less than the allowable strength of the materials. Only then the screw rod is safe. So we can give the screw rod with this particular specification. So we'll take a diameter 40, pitch 7, and it's a square thread here. So this is the design or selection of this square thread for the power screw or screw rod for this particular screw jack. Coming to the head now, that is the thrust collar and handle. So this is the collar and this is the screw rod and this is the handle bar. So to design this now, so the thrust collar we have seen in the previous session, the collar friction and all, so that will apply now. So the dimensions of collar is, so we have this collar, so we have this D1 dash and D dash and D1 dash. So this is the height of the collar and this is the head or collar head. This is the handle here and this is the diameter of the handle, DH. So D dash, larger diameter, this one is taken as 1.5 times the diameter of the screw rod. So screw rod diameter is 40. So relative to that we calculate it as 60. And D double dash is small diameter, so that is 0.5, half of that 40. So we get the diameters D dash and the D1 dash for this D dash and D double dash, larger diameter and smaller diameter of the collar with respect to the screw rod diameter. So this is the screw rod diameter, 40 mm. Just now we had taken this. And mean collar diameter, again we have seen that in the derivation. You can calculate with the uniform wear theory and uniform friction theory. So if you take the uniform wear theory, the mean collar diameter is the ratio, that is the sum of the external diameter and internal diameter by 2, larger diameter and smaller diameter by 2, and coefficient of friction at the collar is 0.12. You can assume this, and so once we know this these two, DC and FC, we can calculate the torque required to overcome the friction at the collar. So this equation we have derived, it's there in the data handbook, so you can directly calculate the torque required here. So once the torque required due to at the collar is found out, we have to add the torque at the screw rod and the torque at the collar here. So to add all both the torques and you will get the total torque as 256 kilonewton millimeter. So this is the collar torque at the collar. So TC, it has to be added to the actual collar, actual torque for the screw rod. So that becomes the total torque to be required to lift the load. Coming to the length of the handle. So length of the handle, you are applying, the handle is there and you are applying the manual load, so perpendicular to that, or what is called as effort. So usually for a normal average person, a labor, around 400 Newton is applied. So length of the rod is taken as well. So the load applied into length will give the torque. So we can calculate the length of the rod. So torque is nothing but the total torque. Just now we found out total torque required is 256 kilonewton millimeter. So that we are applying here, and the load, the average load of a person is 400 Newton. So you can calculate the length of the bar. So length of this bar will be, the length of the handle bar will be 640 millimeter. And diameter of the handle, so you can again take it from the bending equation. So it is 640, that is the length of the handle, minus 30 mm into 400 mm will give the bending moment. So with respect to the bending of the rod, we will calculate the moment. So taking the bending moment equation, you can calculate the bending stress in that rod. So once the bending stress is known, you can calculate we'll get the diameter of the handle. So the metal, since it is bending stress is known, it is taken as 82 megapascal from the data handbook. So you can calculate the bending moment as the length into distance. So that length of the handlebar into the load applied, force into distance is taken there, and you can calculate the bending stress as 82 megapascal. So this is from the data handbook you can get this for that material, and you can calculate the diameter of the handle by this bending equation. So that rod, it has to be designed for bending moment. And this is the height of the collar. So height of the collar will be equal to 2 times the diameter of this handlebar. So handlebar diameter is 32, so height of the collar will be 64. And coming to nut, so nut again, it is made up of bronze or cast iron, and we can select from the data handbook, you can select the metal property for phosphor bronze as 50 megapascal. That is the allowable tensile strength of the metal is 50 megapascal, and allowable shear stress will be 25 megapascal, and this is the bearing pressure 15 megapascal. So this is the nut. So this is the height of the nut, H is there, and these are the diameters of the nut, and this is the internal thread in the nut. So these are all the diameters: nominal diameter DO, the inner core diameter D1, and DN1 is outer diameter of the nut body. So this is outer diameter of the nut, and DN2, this is the DN2, outer diameter of the nut collar. So this is the nut, actually the upper part is extended, so this is called as nut collar. So on this we will be having the collar, so it is a nut collar here, and Tn is the thickness of this nut collar, and height H is the height of this nut. So height of the nut you can calculate by the bearing pressure. So that bearing pressure PB, just now you have taken that. So the bearing pressure for this material will be 15 megapascal. So that is substituted here, and since the diameters of the nut is having 2 diameters, so you can calculate the bearing pressure by force by area into number of threads. So number of threads is 7, the bearing threads is 7, so you can calculate that to 7, and you can get the what is called as, so number of threads you have to calculate. So if bearing pressure is known, weight is known, diameters are known, so you can calculate the number of threads. So number of threads is 7 here. We get 6.98. It is equal to, we can round it up to 7 threads. And since threads into pitch, so pitch is 7 and number of threads is 7, so height is nothing but 7 into pitch into number of threads. So height of the net will be 49 millimeter. So once the bearing pressure of the nut is selected, you can calculate, and the load is known, diameters are known, you can calculate the number of threads in the nut, which is actually in contact with the screw rod here. So that will give the number of threads, and number of threads into pitch will give the height of the nut. So nut height should be 49 mm. So this height of the nut will be 49 mm. So this is the length where the screw rod and the nut will be in contact. So there will be 7 threads inside this length of this nut here. So 7 threads will be in contact between the screw rod and the nut internal diameter. So again you can check the design here. So shear stresses in the threads. So the root thickness of the thread is P by 2. So you can calculate the shear stress force by area. So the load is, force is nothing but the load applied, and the area of the square thread is pi d1 n2 n into t. So this is the number of threads into thickness. So this you can calculate the shear strength, that is the strength at the thickness of the thread here. So it comes to 16.53 megapascal, and it comes to, again you can calculate the shear stress in the nut. The same formula holds good here, and you can calculate the shear stresses in the threads. So this is the shear stress of the thread, and you can see that induced stress is less than the allowable stress. So 13.62 megapascal and 16.536, they both are less than the allowable shear strength. That means your design is safe. So you can calculate the shear stress at the threads of the nut, where you are taking diameter d0 of the thread nut here, and in this case we are taking d1 of the thread. And based on this you can calculate the outer diameter of the nut body, that is 2 times the d0. So you can, it is multiplied by 2, and thickness of the nut collar you can have from this equation. So it is there in the data handbook. So actually this is tau here, it's not pi n, it is tau. So based on the shear stress you can calculate the thickness of the nut collar here. It comes to 7 mm. And dn2 also you can calculate by compression consideration, because the load is applied on that nut collar. So again you can take the area, force by area with the 2 diameters, and you can calculate the dn2 value. It comes to 87 millimeter. So this is about the nut. Okay, so nut, when you design, the nut has to be designed for these dimensions: dn2, thickness of the nut collar, then internal smaller diameter of the nut collar, and d1 and d2 are related to the screw thread. So all these dimensions you can get it from the data handbook equations. So go on using the equations, corresponding equations, and you can calculate the height of the nut, and you can calculate the stresses, shear stresses at the root thickness of the thread, and also you can calculate the shear stresses at the threads of the nut, and they should be less than the allowable shear strength of the material of the thread of the nut. So this is regarding the nut here. So nut we are using material as phosphor bronze, and for phosphor bronze the allowable shear strength and normal strength or the direct stress is so much. We have taken this, so the stresses, induced stresses, should be less than these values. Otherwise, if they are more, induced stresses are more, again you have to redesign. So all these equations are there in the data handbook. You can take these corresponding equations and you can calculate the thickness or the dimensions of the nut here. And coming to the body, the frame, so you know that cast iron is used because it's a compressive load. The cast iron is it is having very high compressive strength, so usually the frames of the screw jack is made up of cast iron, and it is the drawing you are done, it is tapering dimensions to provide the proper stability when the load is applied. So this is the lift. So this is the lift of the screw rod, and the ground clearance, you have to give some ground clearance. So, and the height of this nut collar is there. So add all these things, you'll get the height of this frame here. So height of this frame is equal to lift plus this collar height, nut collar height, and you have to give some clearance. So you can assume some clearance 20 mm or 25 mm, and that will become the height of the frame here, screw jack frame or the bottom support. So coming to the efficiency, again you can calculate the efficiencies. The formula is there, and when you calculate the efficiency, since the design is safe and all the dimensions are already taken, so it will be less than 50%. So if you calculate the efficiency for this screw rod, if it is less than 50%, then it is self-locking. So when you calculate the efficiency, it comes to 16%. So it's a very well designed screw jack. So it is self-locking, condition is satisfied. That's what is required in the screw jack. And coming to the cup, so cup is again made up of cast iron, and we can proportionately fix the dimensions of the cup here. So that's it for this session. So we have referred different textbooks for this understanding this particular design of power screws, and we used a design data handbook, Mahadevan and Balavi Reddy, Dr. Lingaya and Narayan Iyengar. So these are the data handbooks we can use. Some textbooks are there which are authored by Maliv and Atmans, and we have V.V. Bandari also, and we have Parasdak Haideri. So different textbooks are available, and different data handbooks are available. So we have referred all the data is taken from these books. So thank you for listening all the sessions, and I hope with these sessions you can design the screw jacks, or particularly power screws, for different applications. Thank you.